A telescope at f5 focal ratio does not record an extended object faster because light moves faster through the system. It records it faster because the same collected light is concentrated more strongly at the focal plane. That is the physical distinction this episode establishes. Hello everyone, this is Farzad and welcome to the 5th episode of Austronomic. In the 4th episode, we established that focal length sets the physical scale of the image at the focal plane. In the 3rd episode, we established that aperture determines how much light the telescope intercepts. Focal ratio connects those two quantities. It is defined as focal length divided by aperture diameter, using n for focal ratio, f for focal length in millimeters, and d for aperture diameter in millimeters. N equals f divided by d. This is the ratio written on an optical system as f/6.9, f/7, or f/10. For example, the ASCO 71F has a focal length of 490 millimeters and an aperture of 71 millimeters. Its focal ratio is therefore 6.9. This is written as f/6.9 and read as f6.9. Slash is omitted in the speech. Focal ratio is not a separate physical property added on top of aperture and focal length. It is the ratio formed from them. That ratio also has a direct geometric meaning. Light entering the aperture converges towards the focal point and forms a cone. A smaller value of focal ratio, known as n here, produces a wider cone with a larger convergence angle. A larger value of n produces a narrower cone with a smaller convergence angle. The photographic terms fast and slow here come from that geometry. They do not refer to a speed of light or any mechanical speed. They simply refer to how quickly signal builds up at the detector for an extended source. Now consider a small patch of an extended nebulae that covers a fixed angle on the sky. The aperture intercepts photons arriving from that patch. The rate at which those photons are collected is proportional to the aperture area, so it scales as d squared. Those same photons then form an image of that patch at the focal plane. If the focal length is increased, the image of the same angular patch becomes larger. Its width and height increase in proportion to the focal length. So the total image area scales as f squared. The key point here is that the total collected light from that patch has not changed. It is the same collected light, but as focal length increases, the light is spread over a larger area at that focal plane. That means the light is less concentrated at the detector. Now it's a time to talk about irradiance. Irradiance is the photon flux per unit sensor area. So if the collected photon rate scales as d squared, and the area over which that light is spread scales as f squared, then the irradiance scales as d squared over f squared. Since n equals f over d, as we already discussed, this becomes 1 over n squared, 1 over focal ratio squared. So for an extended source, focal plane irradiance scales as the inverse square of the focal ratio. This is the central physical result. If the focal ratio is reduced by a factor of 2, the same collected light is concentrated into 1/4 of the image area. The irradiance therefore becomes 4 times larger. We can now state the governing relationship directly. Irradiance E is proportional to 1 over n squared. Here E is the photon flux per unit sensor area at the detector, and n is the focal ratio. This shows that for extended source imaging, aperture and focal length enter together through the ratio. In this specific result, It is that ratio rather than either quantity on its own that governs the irradiance formed at the focal plane. At this point, exposure efficiency can be defined clearly. In this context, it means how quickly an optical system builds signal at the detector from an extended target. That rate is set by the focal plane irradiance. Irradiance is the optical power received per unit area at the detector. So if more light is concentrated into each unit area of the sensor, the signal builds more quickly. If the same light is spread over a larger area, the signal builds more slowly. For an extended source, a lower focal ratio therefore means higher focal plane irradiance and greater exposure efficiency. The time consequence then follows directly. If a certain signal level is required, lower irradiance means the detector must integrate for longer to reach it. That is why the required integration time scales as n squared. In practical terms, doubling the focal ratio requires 4 times the integration time, while halving the focal ratio reduces the required time to 1/4. When different systems are later compared, the focal ratio effect should be isolated by keeping the rest of the relevant imaging conditions fixed, such as detector response, filter transmission, and target class. If those differ, their effects must be treated separately. The clearest worked example is one where the aperture stays the same and only the focal ratio changes. The ASCO 103 APO has a native focal ratio of f6.8. With its 0.8x reducer installed, the focal ratio becomes f5.44. The aperture remains 103 mm in both cases. So the aperture configuration is unchanged and the local ratio effect is isolated. Using the integration time scaling, required time ratio equals 6.8 squared divided by 5.44 squared makes it 1.56. So the native f6.8 configuration requires 1.56 times the integration time of the reduced f5.44 configuration to reach the same signal level on an extended source. Equivalently, the reduced configuration completes the same imaging task in about 64% of the time. That is the correct interpretation of what the reducer is doing here. It does not increase the aperture. It does not make the telescope intercept more photons. It changes how the image is distributed at the focal plane. In the system with the reduced focal length, the same collected light is concentrated into a smaller image area. So the irradiance at the detector increases. At the same time, the shorter focal length makes the plate scale coarser, meaning that the same angular patch of sky is distributed across fewer pixels. This result applies to extended sources only. For unresolved stellar targets or planetary imaging, the story is completely different. Extended sources, unresolved stellar targets, and planetary targets must each be treated separately, because focal ratio does not play the same role in all three cases. For an extended source, focal ratio that determines the exposure efficiency is the primary factor. Each pixel records light from a finite angular patch of sky, and the recorded irradiance depends on both how many photons the aperture collects from that patch and how large its image becomes at the focal plane. Aperture and plate scale here still matter, but for different reasons. Aperture sets the underlying optical resolution limit, and plate scale sets how the image is sampled across the detector. For an unresolved stellar target, aperture is the governing parameter for signal collection. The sensor records the point spread function, not the star's true disk, and the total collected stellar signal is set by the aperture area rather than by the focal length. Focal ratios still matter, but it is not enough by itself. In this regime, Plate scale must be matched to the seeing disk so that the stellar image is neither undersampled nor spread across more pixels than necessary. For a planetary target, aperture is again primary because it governs both photon collection and angular resolution. Focal ratio is also a priority here, but in practice it is usually balanced against the plate scale needed to record fine details on the detector. So the practical rule is clear. For extended targets such as nebulae, emission regions, and resolved galaxies, focal ratio that governs exposure efficiency is the most important criterion. For unresolved stars, planetary targets, and basically all the compact targets, focal ratio still matters, but it is not sufficient on its own. Aperture and plate scale must also be chosen to match the angular detail the system is meant to record. Now we can place this in the broader instrument trade study. The ASCA 71F at f6.9, the ASCA 91F APO at f6.7, and the ASCA 103 APO at native f6.8 all lie in a narrow exposure efficiency band of focal ratio. Their deep sky imaging differences are therefore driven more by plate scale and field of view than by focal ratio alone. The non-obvious result appears when the 0.8x reducer is applied to the ASCA 103 APO. At f5.44, it becomes the fastest extended source configuration in the instrument set on this metric. This is especially clear when it is compared with the reduced HHD systems. The reduced HHD 800 and reduced HHD 9.25 both operate at f7. Even though they have much larger apertures, they still require more integration time for the same extended source signal level than the reduced ASCA 103 APO at f5.44. That is the key engineering result of this episode. For extended source exposure efficiency, focal ratio is the parameter that separates these configurations, not aperture alone. In this episode, focal ratio was defined as the ratio of focal length to aperture. For an extended source, irradiance at the focal plane scales as the inverse square of focal ratio, and the required integration time scales as the square of focal ratio. Aperture, focal length, and focal ratio therefore play different roles. Aperture determines how much light is intercepted. Focal length sets image scale, and focal ratio determines how efficiently an extended image builds signal at the detector. The EP5 journal in the GitHub repository contains the full derivation, the complete trade study, and the experimental procedure for testing these predictions against real imaging data. The next episode addresses atmospheric seeing, the mechanism by which the atmosphere limits the angular resolution any ground-based optical system can achieve.